The elephant in the room when it comes to Houdini 18.5's new features is clearly KineFX, a soft-spaced rigging kit that SideFX has been developing. And while I'm typically not that enthusiastic about rigging, this one I find quite intriguing, because it allows you to create procedural rigs, and thus use and abuse KineFX to build setups which deviate from the well-treaded paths of rigging humans or human-like characters. Before we get started, I'll have to point out that Matt Estella has outdone himself as usual and did a neat write-up of the major features in KineFX available on his CG wiki. And in fact, we're going to start out with one very simple example that Matt does on his wiki, just dropping down a geonode, diving in there, and as well dropping down a line, like so. Make sure it's 10 points and feed that into KineFX's skeleton. And hit stash input. Houdini will notify us that clicking stash will clear all existing edits. I don't want to see this ever again, and hit OK. So what this has done is internally it built a joint chain out of these individual line segments here, giving each of those points a local transform with which we can rotate or move around our points in this joint chain. Let's demonstrate what I mean using the rig attribute wrangle, a new wrangle in Houdini 18.5, designed specifically to run over KineFX rigs. So in here, what I want to do, I want to take this attribute here, the local transform, and rotate this. So I'm going to rotate my local transform, which is a 4x4 matrix. So 4 at local transform, loads up my matrix, and rotate will also write back this modified value we're going to be generating here. Let's just look up which arguments rotate takes. So it takes an amount and an axis around which you want to rotate. So in our case, let's just use the time and maybe scale it down a bit. And we want to rotate, let's say around X, 1, 0, 0, like so. And now if I toggle real time and hit play, you can see that this joint chain is bending as expected. All right, not too exciting. So let's build upon this and feed this some more complex procedurally generated curves. For that, I'll load up a file, which I downloaded from 3dscans.com, which comes in a bit too big and also not centered. So let's use first the match size and scale it to fit a 1x1x1 box, but scale it uniformly. Just get rid of the point display here and flip this around by attaching a transform. And in the transform, let's rotate this 180 degrees around the X and Y axis. So this is this lady's head that I'm importing here. Normals are flipped, so let's attach a reverse sop. And now we got proper normals. However, this mesh is a bit too high res and also not uniformly sampled. So let's resample this with a remesh node. And the default setting of a target size of 0.2 might be a bit too coarse. So let's set this to 0.02. And after a bit of calculating, this is our mesh. Let's give this normals. In our case, I want this to be point normals. Now, as you've already seen, what I want to do is peel those individual polygons off of the mesh. And for that, I want to generate a rig, a skeleton, with each of its individual points at the center of those triangles here. And to generate this skeleton, we'll first drop down a divide node and calculate what's called the dual graph of this mesh here by checking compute dual in the divide node, which will give you this hexagonal and pentagonal grid. And if we ghost the normal node over this, we can see that the points making up the dual mesh here are always in the center of those triangles of our original mesh. So I want to use this dual mesh here to generate my lines for my skeleton. And to generate those lines, I want to use the trusty old shortest path growth, for which I'll need starts and endpoints. So I'm going to use a group node. Wire this below the divide, set this to be on points and call this one start. And I want to use the keep in bounding regions method of selecting which points are in my start group here. So in my case, I'm going to set this to be a bounding sphere, make sure I have my tool handles checked, and then let's move this over to this side down here, maybe somewhere around here. So we are at this bottom edge of our statue here. And let's just scale this back to 0.1, 0.1, 0.1. Whoops. Like so. Let's just check. So yeah, that is not the correct position. Somewhere around here. So those are our starting points. Next, let's drop down another group node. Again, setting it to points. This will be the end group in which all the endpoints are. And we want to enable anything but our start point. So exclamation mark start. Let's select anything but those start points here. Okay, start and end group are selected. Time to drop down our shortest path. Goes below the end group. It's highlighted and set its start points to the start group and its endpoints to the end group. And under the output path, select from any start to each end, like so. And now we generated those individual paths, all growing from this lower back corner here. Now, when I enable the display of the point numbers here and zoom in a bit, I can see that on many occasions, points are overlapping. That is because the find shortest path node creates individual paths from a start to each end node. That means we have lots and lots of overlapping paths, for example, in this area here, which branch later here or maybe there. And for my skeleton, I want those paths to be all fused together to form one path. So anything that's originating at one start point is fused together to form a single path. To do that, I'm going to just use the fuse node, wire that in down here, and the default settings should be fine. Just middle mouse on this, so we have around 9,300 primitives here and around 9,300 points. When we compare that with the find shortest path, we can see we reduced this down quite a bit from over 500,000 points previously. We might feel tempted to take these paths and now just straight up wire them into a skeleton node. And you can try that, but before that, save your file, because this, in the best case, will result in an error message. In the worst case, it'll crash Houdini. Because not only, when we middle mouse on this, do we have a grotesque amount of vertices still in our geometry, but also we are bound to create some cycles. Or we are generating paths in here whose direction is not always pointing forward, which will confuse the skeleton node here as it tries to build its rig. So to fix that, there are quite a few steps involved. Let's go through them one by one. The first thing I want to do is, on those points of my individual paths here, I want to write a distance value. It means how far from the starting point each individual point is. And for that, we can use the very handy edge transport node, which I'll wire in below the fuse here. And when we highlight this, go to this node here and open up its help tab, we can see when we scroll down here a few recipes. And we want to compute the distance along the curve at each point. So these are my settings. We set the direction to forward, operation to total, integrated constant value, and scale by the edge length. We could set this to edge network as well. Then it would be important to set the edge split method to copy. Let's leave it at that. Next, I want to promote this attribute from our points to our primitives. So using an attribute promote, let's promote from point to primitives the distance. And let's make sure we don't delete the original attribute on our points. Also, for later, if I want to turn this into some sort of veins, it might be handy to have the minimum and maximum distance value available. It's not really needed to build a skeleton. Just for now, I want to copy this attribute promote, set this to promote to a detail attribute, change it to a new name, call this one max, and set the promotion method to maximum to get the maximum distance value. Also copy this node one more time, wire it down here, and set its promotion method to minimum and the new name to min. So now we have the minimum and maximum values for distance written as a detail attribute. So when I middle mouse on this, I can see max and min as a float here. And also I've got my distance as a point attribute and a primitive attribute. Next, we're going to sort our points and primitives by this distance attribute. Using our sort sub, and we want to sort our points by an attribute as well as our primitives. In both cases, the attribute is called distance, and that should be good. Now, finally, we can drop down a polypath and turn those overlapping vertices and overlapping paths into single connected paths. So if I attach the polypath and middle mouse on it, you can see we have now around 10,000 vertices, and before we had those 650,000 vertices. So that worked. I think now we're ready to wire this into our skeleton. So it goes in here, let's highlight this, just hit dash, and yes, don't ask me about this again. Now when I middle mouse on it, I have all those skeleton and rig attributes on my points here. So now what I can do is go to my old setup and just copy this rig attribute wrangle where I rotated each joint depending on time and paste it down here and wire it up. Let's just save this, highlight this, make sure I have the real-time toggle checked and hit play. And well, you know, that does something. And in a way, you could argue that it works. However, currently what we're doing is we are rotating every single joint around the x-axis. That's this vector we manually entered here. So if we want to unfold this mesh to the outside direction, we'd have to calculate an axis that would have to be orthogonal to the normal direction, so that it's not pointing outwards, but it's orthogonal to it, as well as orthogonal to this curve's direction. And we can calculate such a vector if we have both our curves tangent, that means the direction of the curve, and the point normal. Let's just check our geostream. So before we feed that into the skeleton here, we have neither a normal nor a tangent. The tangent is easily fixable. Before we wire this into our skeleton, let's attach a resample node. Make sure to uncheck the maximum segment length. We don't want to generate new points. We just want to abuse this node. Let's check this down here to generate a tangent, and maybe later for shading or for modeling individual veins on here, a curve U attribute. Wire this in here, and that worked. Now to update my skeleton, I need to click stash input again. However, when I middle mouse on this, I still don't have normals. So let's go up, because I'm pretty sure that up here we created point normals, and see at which point they disappear. So directly after the normals we attach the divide, and this already promotes the attributes to prims. So let's instead attach another normal below that divide. Set this to generate point normals again. So now we have point normals again. Group doesn't do anything. Find shortest path kills my normals again. So let's do this and be cheap today. And right before the resample, add in an attribute transfer. Wire this in here, and up here after we divided this thing, let's take this normal node here and put that in the second input slot. Let's alt click on this connection here just to kind of clean this up a bit. Put this wire on the outside, and in the attribute transfer I want to uncheck my primitives, and for my points I just want to transfer the normal attribute. So when I middle mouse on this, I've got my normals again. Let's just highlight this and display the normals. And yes, that looks like proper mesh normals. Also, let's just highlight the resample here and to it attach a visualize node, so we can show and check if we have our tangent U set correctly. And yeah, this is quite long, so let's dial back the length scale here. That when we zoom in, looks like a bunch of vectors pointing roughly in the direction of my curves here. Perfect. Okay, let's hit stash input again on the skeleton, and now we also have a tangent and our normal. So let's use that in our rig attribute wrangle to calculate this axis around which we want to rotate those individual joints. So we want to create a vector that is orthogonal, that means right-angled, to both our normal and the tangent. And to do that, we can use the cross product. So let's create a new vector, call this one dir for direction, and it should be equal to the cross product of our normal and our tangent U. Now let's just take this directional vector here, dir, instead of the x-axis, to do the rotation and hit play. And that goes into the wrong direction, so all we have to do is give this time here a negative sign, and now it should be curling outwards. And it does. However, one thing that's not correct here is that those individual lines are not fused yet, so they fall apart, as you can see, into those individual strands here. To fix that, let's, after the resample, wire in a fuse again to fuse those points together that we just created. And now we have to move this attribute transfer out from up here and down below the fuse, because we changed our geometry stream by fusing different primitives together, like so. Let's save this on our skeleton, hit stash input again, and now let's hit play. Now we can see that this animation is quite quick, admittedly, so let's dial this back, but we have this peeling effect here. However, this effect is quite uniform currently, so why not use the distance from the original point that we saved when we resorted this whole rig here to drive the strength of rotation? Let's just middle mouse on our geostream, and in here we still have our maximum and minimum distance saved, and also our distance as a point attribute. So let's just do this. Let's create a float called d for distance, and for it, let's fit our current distance. It's written on our points, which originally is between the minimum and max, which we'll have to look up in a second, and refit it to be between, well, in this case, let's just go with a range of 0 to 1. So my max and min isn't specified yet. Let's look that up as well. So create a float, call it max, and it's the detail attribute saved on our incoming geostream here called max. Let's just copy this line here, paste it, and do the same thing for our min value, which will look up the min detail attribute. That seems to work. So now to our time offset here, let's multiply this, for example, by our d value. And now we can see that on top here, the further we get away from the starting point, the more our mesh curls. And there would be different expressions. I could, for example, square this distance here to make this effect even more pronounced, or I could use a ramp node to drive the strength of this effect. In my case, let's just stick with the simple D. And now let's talk about deforming the original mesh that we have up here in the remesh. Let's just get rid of those few other nodes that are still left over. As this is quite an unconventional setup, the quickest, that means most performant while still stable solution I found involves a bit of Vex instead of relying on any of KineFX's built-in tools. So to deform these individual polygons, first what I want to do is split those into individual polygons using the facet sub, for example. And in the facet sub here, let's check cusp polygons, setting this to a cusp angle of 0. So now we split apart those individual primitives into individual polygons, which we can now move around. Let's drag this all the way down through our node chain here. And what we're going to write is somewhat similar to the point deform vex code that we talked about in those Houdini on mushrooms videos. So let's drop down a primitive wrangle, wire our faceted geometry in the first slot, and then we need two other inputs, our original skeleton here and our deformed skeleton here. And also I want to know for each of those individual primitives here, which of those points in my skeleton is the closest point to each primitives. So before we care about deforming this geometry, let's drop down another prim wrangle. Facet goes in the first, skeleton in the second slot. And in here, I just want to find the closest point to a primitive's center that lies on this skeleton geometry, which we're going to do with a quick expression. So let's call this one npt for near point equals to near point on our second input geometry, ID1, at our currents primitive center v at p. And let's write this out as an integer attribute. Again, call it npt, like so. Let's just go to the geo spreadsheet and check on our primitives. We have this npt number here. Perfect. So onto our prim wrangle here, which is the deform. Let's call this one find near point, and this one deform. So the first thing I want to do is I want to calculate the offset between this skeleton here and the deformed skeleton here. So in here, I will look up 2 point positions. First, let's call this one the old position or the original position. That's the position of my near point that I found coming in through the second input slot. So the one with the ID1, and the attribute we're looking for is called P for position. Let's just copy this line, paste it down here, call this one npos for a new position, looking up the position of that same point on our third input slot, one with the ID 2. Let's calculate the difference between those two, so basically the offset. Call this one diff for difference, and it's the new position minus the old position. So what I could do now is find out for each primitive which points it has, and then just offset those points by this difference here. Let's try that. Call this one maybe PTS, it's a list of points, namely the points that make up this individual primitive. Primitive on our first geostream here with our current primitive number. And then for each of those points, let's get its position, call this one pos. So again, first input slot here, trying to look up the position of our current point we're iterating through. And these individual points come from this list here. Next, let's add to this one the difference we just calculated and write it back to the point. So set point attrib, first geostream attribute is P, point is PT, and the value of it is pos. So now you can see that it's somewhat working. And we're taking into account the position of those deformed splines here, of this deformed rig here. However, when you look closely, we're not taking into account the rotation. So those individual triangles, in my case, they just stay oriented the way they were originally. Let's fix that by, to this beautiful code, adding a bit of linear algebra using a few matrices. Don't worry, it's quick and rather painless. So similarly to what we've done here, calculating the difference in position between this undeformed and this deformed skeleton here. Let's skip a few frames, so undeformed and deformed skeleton. Similarly to how we calculated the difference in position, we want to calculate the difference in rotation that we have. And the rotation on my skeleton is stored in an attribute called transform. And as you can see, it has 9 floats, so it's a 3x3 matrix. So let's just copy these 3 lines here, paste them, and instead of vectors, let's create matrices, 3x3 matrices, and maybe call them old X form, new X form, and diff X form. So we're looking up not the position attribute, but the transform matrix on both the undeformed and the deformed geometry. And now to calculate the difference, we cannot just subtract these matrices. We have to be a bit more intricate about this. And the way this is done is by inverting the old transform and multiplying it with the new transform. So that'll give me the difference between those 2 rotational matrices. To apply this rotation now, in this loop here, where we are transforming our individual points, again, we will have to be a bit more clever than just multiplying this matrix on these individual positions, because we have to move those individual point positions to the center of our world first by, from our current point position, subtracting our primitive position So basically what we've done now is, using the triangle here, is we moved those individual primitives all to the center here. Now we can rotate them by multiplying our position with our difference in the transforms. And now we can move back our points to their original position and also applying this positional difference. So we could do that in one line by just adding this v at p here, like so. Or if you're more into better legibility, let's just transform them back to our original position first and then apply the translation difference here. So that's our original mesh. Let's save this, cross our fingers and hit play. Now you can see, apart from this one sucker back here, that is working really well. And this error back here, in my opinion, comes from this facet node here, which isn't doing its job properly. So instead, let's use a vertex split. Let's disable the facet, and we're in the vertex split instead, and uncheck the attribute here. So now that's gone, we're splitting our geo into individual polygons here and then deforming it here. All right, for the animation that I created, what I did is I fed this animation into a vellum solver. So back here where we're getting these protrusions, meshes intersecting, the vellum solver tries to get rid of that a bit. And you can see in the supplied scene file how I set that up. I won't go over it now. I think it'll be past the scope of this tutorial. However, what we could do is, after this rig is deformed here, we could turn this into kind of veins. And for that, I don't need most attributes written on here. So I'm just gonna delete everything I have here except my distance on the points using the hat symbol that excludes anything from deletion. And I think I don't want to delete the detail attributes. So now I still have a distance and my max and min distance. Perfect. Next, I want to use this max and min distance and the distance to create a p-scale attribute. For that, I'll just drop down a point wrangle. And just going to take this code that I've written in the rig attrib wrangle here, where I'm fitting this distance and looking at the min and max, pasting this down here. I don't need the cross product for the direction. And this time I'm going to write this fitted d value onto a p-scale attribute, like so. Then I'll feed this into a sweep node, which I'll set up to be a round tube, maybe with 12 or 16 columns. I want to add a gridded end cap, which also has some roundness to it. And let's dial back the radius here. And you can see we have gotten our p-scale attribute exactly the wrong way. And if you think about it, that's logical. Where the distance value is low, where we're really close to the original points, the p-scale is low. And where we're far away from the original points, our distance is high, and thus our scale is high. So let's reverse that in the point wrangle by just switching around those values back here, so remapping them from 1 to 0 instead of 0 to 1. So now my veins grow into the right direction. And now let's just combine those using a merge, our deformed geometry and the veins. And now we have this here. All right, lots to take in. Bit of funky linear algebra here to get those transforms out. Bit of path wrangling, resorting, redrawing, fusing, and finally attrib transferring to clean up these original paths here to give them back some of their original point attributes, such as the normal. But then the skeleton really does the heavy lifting here, building this whole rig that we can then deform using the rig attrib wrangle with those few easy lines of vex. Let's just delete this facet node we don't need here anymore, maybe add a new in-between point here and zoom out, and that's quite a substantial graph we built this time. So I think it's time we can lean back and be a bit proud of ourselves and think about what we want to use this rig for or this technique for. And as always, if you create any artwork using this technique, don't be shy sharing it. And if you want to know more about Houdini, get access to in-depth tutorials, or just plainly want to support us, consider becoming a patron of ours. And to everyone already supporting us, thanks so much, guys. Without you, Entagma just would not be possible. And a very special thank you goes out to Patrick Fillion, Important Looking Pirates, Rafik Anadol, and Chris Hebert. Thanks so much, guys. So until next time, as always, it's cheers and goodbye.